Good evening, everybody, and welcome to listen to the story of Swan, or how I stopped worrying and learned to build cybersecurity in the maritime world. So, this is a story and play in 3 acts, which begins somewhere in late 2017 and continues until the December of 2018. And how we built basically the world's first autonomous passenger ship in the world. So, what is autonomy in maritime world and what the heck do I have to do with it? Little background. I'm a security generalist, field of cybersecurity from the early 2000s. Previous life in Finnish Navy. Have been a merchant mariner and general tinker, and based on the children's poem, I think what my next career move will be. So in 2017, late 2017, somewhere around October, November, I joined the Rolls-Royce Maritime Research Center for Remote-Controlled and Autonomous Ships, which was established in Turku, Finland, about a year before the event of me joining. I became the cybersecurity lead for a project Swan, which is acronym for Safer Vessel with Autonomous Navigation. So, Project Swan. Previously, Rolls-Royce had a research department in Copenhagen, and the Copenhagen department had been building remote-controlled vessels, but not autonomous vessels. They had a remote-controlled tug called Switcher Hermod, and it was a demonstrator piece for maritime remote control, basically a tug which could be used unmanned or uncrewed as, for example, a firefighting vessel in ports in a case of ship fire or similar accident situation where you don't want to send people too close. The Switcher Hermod was class approved on late 2017, and based on that, Rolls-Royce decided to continue the research for autonomous side of the maritime industry. And as a continuum, the Finnish Turku R&D center started building this one itself. Swan was built on top of already existing hull. It was a Finferry's LA Falco, 54-meter long ferry operating in the Parainen waterway. And Falco was modified extensively to be able to handle autonomous navigation situations. Most importantly, it was redesigned to have a dual azimuth thrusters, 360-degree capable propulsion system. And eventually, this kind of spoils the whole story, but eventually Falco became the first passenger ship in the world with the class approval for autonomous voyage with passenger capacity. So, at this point, we are living in late 2017, and Rolls-Royce R&D gave the kind of ultimate goal for the project to demonstrate the capability for autonomous navigation. And from the very beginning of the project, it was clear that this was a demonstrator. It was not meant to stay in use. It was a piece to show that this is possible. And we started thinking that what is the actual goal for the cybersecurity part of this project. And the whole cybersecurity goal was eventually crystallized in a question: is it safe to continue a current mission? If something happens, is the ship still capable of continuing what it is doing right now? Or do we need to abort the mission? Do we need to start doing some kind of fail-safe procedure? So, a couple of words from the sailor's perspective. My background before joining Rolls-Royce was a merchant mariner, specializing in liquid bulk cargoes, aka oil tankers. And for a sailor, the ship itself is a place to live. It's a place to work. You spend 4 to 6 weeks at a time in the vessel, and you have very little connectivity to the outside world. So already at this point, you can kind of guess that connectivity plays an important role in all these maritime areas. From cybersecurity point of view, the ship is basically just a huge floating power plant and some ICS and OT networks attached to it. Most of the time, quite complicated, most of the time quite old, and connectivity to the outside world from modern, even still modern vessels is MF radios, HF radios, VHFs, satellite connections. If you are close to the shoreline, perhaps mobile networks. That depends on the location. But for the sailor, that's the lifeline. Having a connection to your family, having some kind of connection to the outside world. And this is the kind of a discrepancy between the sailor point of view and the cybersecurity point of view in the maritime side. So, before we actually started building anything, we started defining what actually autonomous means. And we came up with kind of a 4 stages or 4 definitions for maritime autonomy at the time. If you nowadays go and Google this stuff, you probably will find more definitions, different kind of definitions, more steps and such. But traditional vessel, traditional ship is automated to some extent. There is autopilot. There are some kind of decision support systems. Of course, ARPA radar, they can automatically track other vessels for you. You have AIS systems that give you information about other vessels. But key point is that seafarers are on board. They operate and control all the systems, and they utilize the automation. That's still even today the most common situation with most vessels. The second stage of path towards autonomy is remotely controlled. Vessel that still has sailors on board, they can take over, they can control the ship at any point when they feel to do so. But the ship is capable of being controlled from remote control center or somewhere else, some other system or some other vessel perhaps. Third stage is remotely controlled vessel without the seafarers on board. Ship is still all the time controlled by human, but not from on board. The human might be again on the shore, it can be on oil platform, it can be on other vessels somewhere else, but not on board the current vessel being controlled. And the final stage would be then, of course, the fully autonomous ship. And the main difference between the fully automated, fully autonomous ship compared to the three other stages is a decision making. The system is capable of making decisions how to avoid other vessels, how to approach a port, basically all those decisions that humans are currently making on board the vessel. Important distinction is that there is a difference between autonomous vessel and uncrewed vessel. These are often they are talked together, they are seen as the same thing, but it's not necessarily so. There are several occasions where the system, the ship itself, might be capable of completely autonomous operation, but still have a crew on board. Good example would be platform supply vessels providing support to the oil refineries and oil drilling platforms. Their mission profiles very commonly are such that they spend weeks and weeks, 4 to 6, sometimes 10 weeks at a time out in the sea. But the mission critical point takes perhaps few days. You're providing the support, some repairs, some supplies, something else to the oil drilling platform, and then you proceed towards the next target. You might have a transition leg that takes several days. And at this point, there might be kind of no point of having a human on the bridge or human controlling the vessel if there are no other vessels around. And the ship autonomous capability can take some of the burden off from the actual crew of the vessel. They can get some rest, they can do something else, make preparations for the next critical mission phase, something else. So some of the vessels in the future, they might be completely autonomous, completely uncrewed. Some other vessels are probably partly autonomous or fully autonomous, but still have a crew on board. These are not strictly set in stone how they will be in the future. One thing that defined what we were doing in the Rolls-Royce was to focus on the safety. In the maritime world, safety is everything. Everything is revolving around the concept of safety, and it is said that Mariner's Bible is called SOLAS. SOLAS is a convention for safety of life at sea. It was written in 1914 after the Titanic incident, and it's one of the defining conventions from the International Maritime Organization that defines how ships are built, how they are operated, how crew is operating on board. And we had to take everything from the SOLAS conventions into account when we were starting thinking, how do we build a ship that is capable for autonomous operations. Also, every ship has to have a class society approval. So in the world of maritime, the class societies are the instances that define when the ship is seaworthy, when the ship is capable of going out to sea. And idea is that we have handed over this kind of inspection responsibility to the class societies so that they are they are same and similar from country to country. So instead of having a ship that is rated good here in Finland, but not seaworthy in Sweden, for example, instead we kind of count on the class society definitions and their approvals. Every crew member, of course, have to be qualified according to the IMO STCW rules. But one of our main kind of, problem points was that these IMO conventions, they don't really tell much, actually anything, about autonomous vessels or uncrewed vessels. IMO so far has made a statement that something needs to be done, but there is no IMO convention yet defining how to build, how to operate, how to man, how to do anything with these kind of autonomous ships. So we started to design for the security. No class definitions at that point yet. DNV from Norway and Bureau Veritas from France started to build their own class definitions for the cybersecurity side around 2018. But when we were building this project and creating the design documents, they were not yet available. They were in draft forms. Of course, we had some influences from them. So we started evaluating the common industry documents, common industry standards, NIST cybersecurity framework, IEC 62443 for industrial standards, ISO, so on. And by chance, we found out that US Coast Guard was actually thinking these exactly the same things. They had taken the NIST cybersecurity framework and started building a maritime profile on top of that. So the maritime profile for NIST CSF became our kind of a guiding document, but still we took some influences from the other documents, 62443 mainly. At that time, we had some idea on design, what we do, what kind of framework do we actually utilize to figure out how to build a secure and safe ship that can operate without human on board. And we realized that Rolls-Royce had a really strong safety culture already. Rolls-Royce is a company that does processes and they do them well. So their initial design and safety process was done somewhere around 1942 for the Rolls-Royce Merlin engine, and it was updated almost immediately after in 1972 for the Rolls-Royce Olympus engine for the Concorde, and they defined that that's good, let's go with that one. But the safety processes were really comprehensive and strong. They used failure mode, effectivity analysis everywhere. They had a HAZOP processes for every component in the aircraft engine, and all these processes were done really meticulously. So we decided to start taking these same processes and mapping them into the cybersecurity side. And we built threat modeling processes in the form to follow the FMICA. We started building risk analyses to follow the same process of HAZOP. Basically, our idea is that build a process that they already know. They are familiar with their safety processes. Build a security process that flows through exactly the same way as their safety process. We had a lot of help from the Rolls-Royce Aerospace our kind of grand old man was the aerospace side cybersecurity lead, Robert Oates, fantastic guy. This way, we actually were able to introduce the cybersecurity model much faster inside the company than we actually anticipated on the maritime side. And then we ran into this ethical and moral dilemma. What to do when the collision avoidance becomes collision assurance? This is a topic that would warrant its own speak on itself. I could probably speak about hours of this. So I won't be diving too deep here, but the main point is that eventually, one day, autonomous or remote-controlled vessel will be in a situation that it cannot avoid a collision. It will have to decide not to avoid the collision, but where do I collide? And no legal frameworks, no regulatory guidances or anything like this exist. And the burden of making that decision lies on the engineers building the vessel. And it's a difficult choice for a single software engineer to decide who one does. Our solution was rather simplified and straightforward. The vessel decided always the path that minimizes the kinetic impact between two vessels or vessel and shore. It's not a perfect solution, but it was at the moment the one we came up with. So, the lesson learned around late 17, early 18 was that safety and security are very closely coupled in maritime environment. And a security incident almost always becomes a safety incident. And I'm pretty sure that this actually applies to many other areas. If we are talking about aviation, railroad, self-driving cars, even probably many factory networks, many areas. So, story proceeds, and we are now living somewhere around early 2018. And at this part, how we actually dreamed that everything would go when we started building things and how we planned it. The initial stage where we are planning everything, we had really wild, all kind of cool concepts, videos, ideas. We presented videos about autonomous drones flying around the ship, inspecting for failures, like eye in the sky situation, all kinds of augmented reality stuff, real-time remote audio from the axis shafts and such. Nothing of this actually became reality. So from the really cool concepts, we kind of backed bit down into the reality. And we started thinking, what are the actual subsystems that are needed for the autonomous system so that we can actually build this vessel? And the immediate answer, of course, is we need to have the autonomous navigation system, the brains of the ship, that makes the decision where to navigate, how to avoid collisions, and so on and so on. But the autonomous navigation system is unable to do anything on itself if it doesn't have decent situational awareness. It needs to have connectivity when it needs. It needs to have some kind of a cybersecurity system. So we decided to call it very into a innovative name, cybersecurity subsystem. But also, engineering needs to be automated so that we can provide enough information from the engineering and machinery space to the autonomous navigation system. Do we have a propulsion failure? Do we have something that prevents us on moving on one direction or the other? The ship needed sensors. We eventually came up with 3 different basic sensor suits. Traditional maritime radars, they are being used for long-range detection, long-range tracking, and in some cases also identification of the targets. But the problem with radar is that it's not nearly accurate enough in short ranges. There is all kind of distortions and all kind of anomalies in short range. It's very good in tracking long-range targets. We needed something else. We needed something to actually correctly track something that was reasonably close to the ship itself. So for that reason, we have had a LiDAR, which was capable of point cloud mapping and creating reasonably good images approximately to 1 nautical mile. Bit depending on the weather and for example, raining caused some problems with the LiDAR. Then we had traditional daylight cameras, infrared cameras, thermals for close range tracking, identification, and classification of the vessels. There, lots of research was done on image recognition, ship classifications, and similar technologies to identify what kind of a target we are actually dealing with in the close range. Is it another vessel? If it's a vessel, is it actually a cargo, tanker, sailing vessel, something else? The security side was, let's say, interesting. Our original thought and idea was to build a unified architecture, unified structure for everything. And quite soon we realized that the ship itself and the shore side remote control stations are so different that they actually need their own individual solutions. The ship, it needs to be able to fail to safe without a human in the loop. If we are talking about autonomous system, it needs to be able to do the fail-safe without human. On the other hand, the remote control station is always crewed. There is always someone available to make the human decision in the end. We started hunting all kinds of solutions. We decided that we need to have an external security operation center. And in the end, we realized that there is no solution for the ship side. So we got all the cool buzzwords. We got AI, we got ML, and whatnot. And remember, this was 2018. Most of the stuff was PowerPointware at that stage during that time. Pretty much nothing worked actually the way they were marketed. And almost all the systems were designed to operate in a relatively standard corporate type of network. They assumed always-on connectivity, which is not guaranteed out in the blue sea. And pretty much every system defaulted to sending most difficult cases to a human analyst. And especially in the case of the vessel side, this was kind of a no-go for us. So we started thinking, how do we build this? We evaluated 5 or 6 different vendors and options. And our selection criteria eventually became the one with the most cooperative attitude instead of best detection rates. So we started designing, started building the system. We need to have fault tolerance, as every maritime system need to be basically duplicated or some other way made fault tolerant enough that it passes all the safety regulations. And we started building containers in the Docker sense and containers in the shipping sense. So the system was containerized and orchestrating the containers and then building that on fault redundant cluster, which was actually built in a shipping container, which was then welded on the deck of the ship itself. And we started thinking, how do we do the security part? This is kind of the safety part, and what do we do with the security part? How do we guarantee that? And we came into a realization that these security products can get us only so far. But the only actually what we consider to be a really effective way of improving the overall security state of the ship itself was to minimize it into so reasonably, as low as reasonably possible. Take off everything that is not absolutely needed. Minimize the attack surface of the vessel itself so that it is as redundant and as resilient as possible. We started talking about DIE rule as everybody knows the cybersecurity, CIA triad, confidentiality, integrity, availability. But those are goals. Those are something you try to get to. Those are ideals. How do you get there? We had already decided that most of the subsystems are running in a containerized environments. They are orchestrated. Honestly, I don't anymore remember who came up with the acronym DIE. Comes from distributed, immutable, and ephemeral systems. And all the systems need to be distributed so that they are available all the time, even if some part of the vessel fails. They are immutable. When the container starts running, it cannot be changed anymore. If you want to make changes, you kill the container and spin up a new one. In the case of, for example, attack situation, you shouldn't be able to make any changes into the currently running part of the system. And ephemeral, kill the container immediately when you don't need it anymore. Spin it up, do your task, die away. If there is no one responding to your attack, you have less attack surface available. And kind of our conclusion is that if you want to do autonomous cyber, it's actually really damn difficult. There is always a situation when the attacker can push your system outside of its design parameters, of its decision limits. And at that point, if there is no connectivity to kind of get the input from the human, what do I need to do at this point? The system is in a fault state that it cannot resolve itself. And these are really tedious problems and tedious situations to solve. Long failure mode trees, hundreds of nodes on the trees, and each and every one of them should end in a state that is considered to be fail to save. In the maritime environment, this kind of situation where the attacker pushes the system out of its design boundary is a situation where the ship can be stranded. For example, in a busy waterway, it can be stranded, floating in a current, some other situation, and we started saying that we are in a business where a denial of service can actually kill people. Any unexpected situation, this vessel tries to make a connection towards the remote control center, but the window of opportunity to actually make the connection so that the officer of the watch on the remote control center can actually take over and remediate the situation can be very narrow. It can be short, and this kind of situation can, in worst case, lead into collision and people die. And of course, we have all the other maritime area problems. Connectivity, as I already previously mentioned, one of our most precious resources in the maritime area, cannot be guaranteed. Out in the blue sea, there is perhaps a satellite. They are very low bandwidth, very high latency links. If you need to make a remote control operation across a link that has 2.5 second round trip time and 64 kilobits of bandwidth, it's basically an undoable situation. At this stage, we started implementing similar procedures that aviation does. ETOPS, fail-safe zones, so if the system cannot resolve the situation and cannot make a connection, it tries to get itself into a safe zone and basically wait to someone come and pick it up. But it's also not always possible. And then, of course, there's the environment. It's a humid, seawater corrodes everything. The ship is constantly rolling. If you have a traditional hard drive, it will fail immediately. There's all kind of shaking and all that stuff. This is a short case of connectivity. It's a scarce resource, and we can't select if it's available or not. And we started thinking that, is there a way of actually working around bad connection? Can we actually make remote operation with a really bad quality slow link? And one thing that we can affect is the computing power on the ship itself and the computing power on the shoreside remote control station. And we have a LiDAR. It can create very quickly, very accurate point cloud image of the target ahead of the ship. We can convert that one into a wireframe. So we have wireframe model of the target ahead of us. We can present that one with the point coordinates and vectors. That can be actually transferred across low latency or low speed, high latency link. And on the receiving end, we can reconstruct the image. It was actually a GTA 5 engine that reconstructed the image. But that gave the remote operator, officer of the watch, enough information. So instead of having a video of the target ahead of the ship, there was a computer-generated image, but it gave the distance to the vessel, it gave the position vector, movement vector, speed, attitude of the target, and it enabled the remote operator to make the decision which way do we start our movement to avoid the collision. So the lesson learned from this stage is work with what you can affect. Don't spend your resources in the areas that are out of your control. Use what you have and use that to mitigate the systems that you cannot affect. And now we get to the late 2018. How it actually went. So, as I mentioned previously, we realized that we cannot use a single similar architecture on the remote control station and on the ship itself. So the project was kind of split in two. We had the Swan itself, and we had the RCS, the remote control station. The building of these setups began somewhere approximately half year before the demonstration day was set up. The shoreside remote control station was built on Turku, on the Finferry's premises, and the ship itself was stationed in the Parainen-Naua waterway. The distance between these two stations was approximately 50 to 55 kilometers, somewhere around that. The Swan, or Falco itself, one part of traditional shipbuilding, new propulsion and such, one part of purpose-built technology. The subsystems that I mentioned earlier were all separated in their own dedicated networks. Separate cybersecurity subsystem was built. It was isolated from the rest of the ship, rest of the subsystems with one-way links. Most of the technologies we used, we tried to select them from commercial off-the-shelf stuff whenever possible. Some of them we had to build ourselves. Following the class regulations, maritime regulations, all the subsystems were duplicated in maritime environment. We talk about left and right, left watch, right watch, and left system, right systems. They are basically identical on both sides. Name comes from this idea that they actually originally were on the other parts. There was a port and starboard systems. Nowadays they don't necessarily are so. Some of the subsystems were not at the time present on the class regulations, like the cybersecurity subsystem, but we used that to further divide the segmentation. The hardware selection for maritime use was a really narrow selection of hardware that is rated to be used on board ships. Most of the stuff was coming from Dell at the point. They were actually making a line of computers that were rated for maritime use. And not just minimizing the attack surface, we also decided that there is no way to actually connect to the ship itself. So the vessel always initiates connection towards the shore. So there is no way of actually connecting into the vessel. A lot of testing. We had 70 seagoing days for testing the vessel. of course, mechanical testing, all kinds of stuff, but also a lot of cybersecurity testing. And many of the stuff we used, integrated navigation system as a prime example, INS has the inertial navigation, satellite navigation, position keeping. These are systems that are not really designed to withstand any kind of cyber attacks. And on several occasions, we managed to find a vulnerability that allowed us to deviate the actual position of the vessel. As a demonstration, we actually watched from our electronic chart display as the vessel drive 35 kilometers inland as the position keeping device failed. And the OT ICS side had a lot of traditional programmable logics that controlled, for example, electricity conduits and such, and many of them were failing. Good thing was that our company working with us was very helpful and fixed these problems. Okay. The remote control station itself was basically a bridge of a ship built inland. It had everything the same that the ship actually, all the knobs and buttons and sticks and everything were exactly the same. But instead of windows, you had several screens overlaying the video view. This became the central connection point for the vessel itself. Also, very highly segmented network, and we decided to separate, not just segment the networks itself, but have two different categories of networks. We had the actual operational networks that had the services needed for the navigation, and then we had auxiliary networks that had this kind of traditional, you have NTP servers and whatnots, and they were then separated in two different categories. Also, extensive testing on this side, but for the RCS side, we actually were able to find outside security testing companies. So we outsourced some of the security testing at this stage to save time, mostly. And we had the F-Secure RDS at that point selected as a SOC provider. So, almost at the end of the presentation, but 2 weeks before the final maiden voyage, 2 weeks time to the December 3rd, and a wild connection to Ukraine appears. We were on the very end of the testing runs. We were basically preparing the vessel already for the demonstration voyage, maiden voyage. 120 people coming on board, making the first autonomous voyage. And our network monitoring says that we have an incoming connection from a Ukrainian server that is identified as very recent command and control server for some malware. Can't remember the name anymore. So at this point, we went into a panic mode. All the Finnish speakers recognized the proverb, kylmä rinki perseen alla. That was me at the time. And at that point, I made the only possible decision left, and I called Dist. And roughly in 5 days' time, he figured out what was going on. Unfortunately, we had a network misconfiguration and an NTP server misconfiguration at the same time, which led into a situation that our NTP made a connection to pool NTP org, instead of Mittatekniikan Keskus in Finland. And it, by chance, randomly selected that breached Ukrainian NTP server. And the network misconfiguration led us into a situation that we didn't see the outgoing package. We only saw the return package, which made us think that it's actually connection initiated from outside. So you can probably understand that we were in a panic mode. So don't do everything yourself. When you need help, call for help. There are always the brighter guys that can solve the problems that you can't. And every possible plan, test it. Because what we found out, Mr. Murphy, it will visit you on every occasion possible. So, December 3rd, 2018, Swan made its maiden voyage, its only voyage. It was clear from the very beginning that this ship was never intended to stay in service. It was a technology demonstrator, and it served the single purpose of showing that this can be done. Roughly 120 passengers were on board. Can't remember the exact amount. Voyage was done on a very bad weather, sub-zero temperatures, snowing, and voyage took a total of 42 minutes, which were the longest 42 minutes in my life. Half of that voyage, the ship was in autonomous mode, no humans touching any controls. Ship made 3 moves to avoid collision. During that time, the sea area was not cleared of other traffic, so there was all the normal traffic in that sea area all the time going on. And the second half was done on remote control mode, and the vessel was controlled from the Finferry's remote control center from Turku. So, I was told I have 55 minutes, it's gone now. Thank you for not falling asleep, and if you have any questions, you can find me at the Elisa Vartila OT Village on the upstairs. Thank you.